Okay, the last section we have for this chapter is going to start off with the trapezoidal rule. Although the rectangular approximations RRAM, LRAM, and MRAM are nice, sometimes they're not very accurate, especially when you don't have very many subintervals. If you imagine us having trapezoids, so connecting all of these heights of our segments here, reaching up to our function, we would have a height here of y0, a height here of y1, a height here of y2, y3, y4, and so on. But in terms of our trapezoid, if I were to say let's find the area of one of these trapezoids, what is the area formula for a trapezoid? From geometry, which you guys know is 1/2 times b1 plus b2, the average of the bases times the height. And in this case, our trapezoid is sort of standing on its side, so the bases, b1 and b2, are really these y values that I just listed out in red. The height, which really is your delta x, b minus a over n. But we are going to go ahead and just call them height. So we could say that the area under the curve is approximated by 1/2 y0 plus y1 times h, plus 1/2 y1 plus y2 times h, plus 1/2 times y2 plus y3 times h, and so on. So how can we clean this up a little bit? We could factor out the 1/2 in the h, and then we have y0 plus y1 for the first trapezoid, y1 plus y2 for the second one, plus y2 plus y3 for the third one, and so on. Let's simplify it a little bit more. Notice how over here we've got the y1s repeating, the y2s repeating, and so on. This y0 in the front kind of sits by itself. So this is really y0 plus 2y1 plus 2y2 plus all the way down till the second from the end, 2y sub n minus 1 plus the last one, y sub n. This will be what we call our trapezoidal approximation. This approximation is equal to LRAM plus RRAM divided by 2. So what if we could approximate the curve with curved pieces? These curvy sections that we're going to approximate it with are going to be parabolas. So what if I took two equal subintervals, let's call it from negative h to positive h. What if we put a parabola over it? You can easily approximate a curve, so like this would be a parabola right here. So what we're going to do is we're only going to look at this two sections at a time. We will have to divide our interval a to b into an even number of n subintervals. And we're going to take these 3 points right here and approximate a parabola over it. And I'm going to label a few other things on here. The height of these, sort of like how I did them with the trapezoids, I'm going to call these y0, y1, and y2, so that the leftmost point would have a coordinate of negative h y sub 0. The middle point will have the coordinate 0, y1, and the top right point here will have the coordinate h y sub 2. So let's say that this parabolic curve has the general equation y equals to ax squared plus bx plus c. Now I'm going to use our given points, which are negative h y sub 0, 0 y sub 1, and h y sub 2. I'm going to plug them in and write myself a system. So I'm going to have y sub 0 equals to a times negative h quantity squared plus b times negative h plus c. Then I have y sub 1 equals to 0a plus 0b plus c. And then y sub 2 will be a times h squared plus b times h plus c. So simplifying this little piece out, I would have y sub 0 equals to ah squared minus bh plus c. I would have y sub 1 equals to c, and y sub 2 equals to ah squared plus bh plus c. Alright, so given this, I'm going to do something a little different. I want you to tell me what y sub 0 plus 4y1 plus y sub 2 equals to. So given these for our y0, y1, and y2, what's y0 plus 4y1 plus y2? That would be ah squared minus bh plus c, plus 4 of the y's, y1s, so plus 4c, plus 1 of the y2s, plus AH squared plus BH plus C. This is going to be 2AH squared plus 6C. So let's come back to that. Heading back up towards our parabola that we have here, you guys know that the integral of this function from negative h to h represents the area under the curve. So I can say that the area under the parabola equals to the integral from negative h to h of my function ax squared plus bx plus c. So let's go ahead and integrate this. This gives me a over 3x cubed plus b over 2x squared plus cx from negative h to h. So this is a over 3h cubed plus b over 2h squared plus ch minus negative a over 3h cubed plus b over 2h squared minus ch. The b over 2h squared terms cancel. Putting these like terms together, we end up with 2a over 3h cubed plus 2ch. Let's factor out what they have in common. Let's take out an h, and actually let's also take out a 3 from our denominator. Let's get rid of that fraction. So what does that leave us? If I factor out an h over 3 from my first term, I have 2a left times h squared. And how about on this remaining part? What, when I multiply it to h over 3, gives me 2ch? Okay, that should be 6c. Okay, remember when you are factoring out, you're dividing, so 2 divided by 1/3 is actually our 6. Now, do you notice anything? Remember I told you we were going to come back to that part up there? Look at that. Do you see this? This is our 2a times h squared plus 6c. Look, that, oops, down here at the bottom, we have our 2ah squared plus 6c as well. And that was our y0 plus 4y1 plus y2. That is the area underneath the curve using a parabola. So that was like this little piece, and that's the approximation of the area under that curve using y0, 4y1, and a y2. So what this brings for us is that if we have successive sections of these pairs of subintervals, then we can come up with a formula kind of like how we have for the trapezoidal rule. So let me try to show you what it looks like. So let's say this is our curve, our function, f of x, and let's say we're going from a to b, and if we draw in, and let's say this is a pair of subintervals. Here's another pair, actually another pair here, and another pair, and so on. I'm going to try and draw in those points for you so you can see. So let's say this is our parabola for the first one. So we would have some approximation for this set. Then we would take these 3 points and approximate it with some parabola here. And this would be our area right here. Then we would take these next 3 points and maybe approximate it with a parabola that opens up this time. That would be these 3. Now if I were to write in the y0, y1, y2, y3, y4, y5, and y6 that we would have used by using the method that I outlined above, I would be able to say that for the pair of subintervals in red, that would be y sub 0 plus 4y1 plus y2 multiplied by your h over 3. This would give you the area under the curve for the red section. Now if we do the green section, that would be y2 plus 4y3 plus a y4. That's the green section. And then the red section would be y4 plus 4y sub 5 plus y sub 6, and so on. So I hope you can see that I can actually combine some like terms here and clean this up and make it y sub 0 plus 4y1 plus 2y2 plus 4y3 plus 2y4 plus 4y5 plus, and so on. And it's going to go all the way till the end and be 4 times y sub n minus 1 plus y sub n. So our pattern here is actually a 1, 4, 2, 4, 2, 4, 1. The trapezoids, if you had noticed earlier, were 1, 2, 2, 2, 1. Well, here our pattern is 1, 4, 2, 4, 2, 4, 1. And remembering that we have the height, which is your delta x, divided by 3, and think 3 because 3 points on our parabola, not a 2. So let's just do a really quick little example. Let's use Simpson's rule with n equals to 4 to find the area under the curve of x squared plus 2x minus 3. So I want to use Simpson's rule with n equals to 4. Now, what is our delta x going to be? Okay, delta x is going to be b minus a over n. So 2 minus 0 over 4. So our delta x, which is also our height, will be 1/2. So using our formula, which is h over 3 times y0 plus 4y1 plus 2y2, and so on, is going to be 1/2 divided by 3 times y sub 0, which is going to be f of 0, plus 4 times f of 1/2, plus 2 times f of 1, plus 4 times f of 3/2, plus, and our last one, 1 f of 2. So 1, 4, 2, 4, 1. And then you just plug in the values into your function and you have your answer. Okay, so Simpson's rule. Unfortunately, there aren't very many examples in your book to work out, but it follows much like how trapezoidal rule works, with the exception of the pattern 1, 4, 2, 4, 1.